Hi guys, welcome to WeTeach. In this session we are going to discuss high pass filter. So in high pass filter there are two types. Passive high pass filter we'll discuss first. So a high pass filter is the exact opposite to the low pass filter which we discussed in earlier session. As the two components have been interchanged with the filter's output signal now being taken from across a resistor. In earlier low pass filter, so we have done like a resistor in series with capacitor, right? So this is the, we'll take output voltage across capacitor, this is R and this is Vn, input voltage. Whereas coming to high pass filter, it is completely opposite to the low pass filter. Now in high pass filter, I'll just connect capacitor here and resistor at output like this. Here it is the capacitor and here it is the resistor, and across resistor we'll take the output voltage, and this is the Vin, which is sinusoidal. Whereas the low pass filter only allowed signals to pass below its cutoff frequency point. Means low pass, if I see the low pass filter gain wave, which will allow at zero frequency. I mean at low frequencies it will allow. Its graph is like that, right? Whereas in high pass filter, the passive high pass filter circuit, as its name implies, only passes signal above selected cutoff point. So whereas in coming to high pass, so signal can be passed above cutoff frequency like this, or it can be drawn as like this. Okay. So by FC eliminating any low frequency signals from the waveform, consider the circuit below. So this is the high pass filter circuit. In this circuit arrangement, the reactance of the capacitor is very high at low frequencies, right? So the capacitor acts like an open circuit. We can write Xc is equal to 1 by 2 pi Fc. So if I reduce the frequency, my Xc becomes increases. If I increase the frequency, my Xc becomes decreases. So a capacitor reactance of capacitor is very high at low frequencies. So the capacitor acts as a like open circuit. So if a reactance is very high and frequency low, this capacitor acts as a open circuit, means it will gets open and blocks any input signal at Vn until the cutoff frequency point is reached. So until reaching Fc, capacitor will block input voltage by opening. Okay. Above this cutoff frequency, the point of reactance of the capacitor acts reduced sufficiently as to now act more like short circuit. So after this cutoff frequency, capacitor behaves like a short circuit. Now in this case, Vin is transferred to output voltage, allowing all the input signal to pass directly to the output as shown in below filter response curve. So if I see the response curve of this high pass filter, so this one. So up to Fc, beyond Fc it won't allow any signal, right? It will gradually increase. So after Fc, it will start allowing the signal after Fc. Okay. Similarly, if I see the phase versus frequency, our graph will be like this. At up to Fc, my phase angle will be started at 90. So after Fc, it will be gradually decreases. So this is the gain versus frequency plot of a high pass filter. So it will simply shown like this. So this is Fc. So high pass filter will block voltage by opening capacitor up to a corner frequency. So after corner frequency, it will allow all signal to the output. The Bode plot or frequency response curve above for a passive high pass filter is the exact opposite to that of low pass filter, as we discussed. Here the signal is attenuated or damped at low pass frequencies, with the output increasing at plus 20 dB per decay or 60 dB per octave until the frequency reaches cutoff point Fc, where the gain becomes R equal to Xc. It has a response curve that extends down from infinity to the cutoff frequency, where the output stays or output voltage amplitude is 1 by root 2 times, which is 70% of the input voltage value, which is or minus 3 dB as the gain from output to input. Also we can see the phase angle of the output signal leads that of input and is equal to 45 degree at corner frequency. So at 45 degree, my phase angle is 45 degree, right? The frequency response curve for this filter implies that the filter can pass all signal out to the infinity. However, in practice, the filter response does not extend to the infinity, but is limited by the electrical characteristics of the components used. So the cutoff frequency point of a first order high pass filter can be found using the same equation as that of low pass filter, which is Fc equal to 1 by 2 pi Rc, but the equation of the phase shift is modified slightly to account for the positive phase angle as shown below. So in low pass filter it is negative phase angle, but in high pass filter it is a positive phase angle. So let us see, cutoff frequency is Fc equal to 1 by 2 pi Rc, where phase shift is equal to phi equal to tan inverse of Xc by R. So that I can write it as tan inverse of 1 by 2 pi FCR. So this is how we will calculate the phase angle. Now gain is nothing but it's a output by input. So output is, so from this circuit, from the circuit RC, this is the V0 output voltage and this is the Vin input voltage. So by applying voltage division rule, V0 is equal to Vin into R divided by total impedance, which is R minus JXC. So that is V0 by Vin, which is nothing but R by Z. So this is. So now at low frequency, if frequency is low, my Xc will be greater. If I take F is 0, now Xc will become infinite, right? So if I take infinite, F is infinite, now Xc will become 0. At low frequency, Xc is infinite, that's why my V out is 0. So if I substitute Xc is infinite, so this will, Z will become infinite, so anything by infinite is nothing but 0. Now at high frequency, Xc is 0, so anything by 0 is nothing but V out becomes V in. Xc becomes 0, now it is simply R by R, which is 1. So V naught is equal to V in. Now if I take example, calculate the cutoff frequency for a simple passive high pass filter with the C is 82 picofarad and R is 240 kilo ohm. So if I will simply substitute in our standard formula of a cutoff frequency, which is 1 by 2 pi RC, that will give us 8 kilohertz. That is the cutoff frequency. Now coming to second order high pass filter, gain again, as with low pass filters, high pass filter stages can be connected in cascaded together to form a second order filter shown. So as earlier we have discussed for low pass filter, similar kind of way we'll do to get the second order high pass filter. So if I see the first stage of high pass filter, I mean passive high pass filter, and this is the second stage of passive high pass filter. So these two are connected in cascade, right? So the above circuit uses two first order filters connected or cascaded together to form a second order or two pole high pass network. Then a first order filter stage can be converted into a second order type by simply using an additional RC network. The same as for second order low pass filter. The resulting second order high pass filter circuit will have a slope of 40 dB per decay or 12 dB per octave. As the low pass filter, the cutoff frequency Fc is determined by both the resistors and capacitors as follow. When I take both stages capacitor and resistors, so the cutoff frequency formula as Fc is equal to 1 by 2 pi into square root of R1C1, R1C1, R2C2. So in practice, cascading passive filters together to produce larger order filter circuit is difficult to implement accurately, as dynamic impedance of each filter order affects its neighboring network. So if I add stage by stage in cascade manner, so it will affect its neighboring network. However, to reduce the loading effect, we can make the impedances of each following stage 10x, means impedance is 10x, like if R1 is 10, now R2 is 10 into R1, and if C1 is 10, now C2 will become 1 by 10 into C1. So if I make this type of arrangement, now there is no effect of loading on the second order high pass filter. So coming to summary of high pass filter, we have seen that high pass filter is the exact opposite to low pass filter. This filter has no output voltage from DC up to a specified cutoff frequency. This lower cutoff frequency point is 70.7% of a or minus 3 dB of the voltage gain allowed to pass. The frequency range below this cutoff frequency is generally known as a stop band. So cutoff frequency, suppose this is cutoff frequency. So this is my high pass filter graph. So below this Fc, this is known as a stop band region. So after Fc, it is known as a pass band region. Okay. While the frequency range above this cutoff frequency is generally known as a pass band. So the cutoff frequency, corner frequency or minus 3 dB point of a high pass filter can be found using standard formula, which is Fc equal to 1 by 2 pi Rc. The phase angle of this resulting output signal is at Fc is 45 degree. Generally, the high pass filter is less distorting than its equivalent low pass filter due to the higher operating frequencies. So compare with low pass filter, high pass filter has a higher order frequencies. That's why there is a less distorting in high pass filter compared with a low pass filter. A very common application of this type of high pass filter is in audio amplifiers. We will use high pass filter in audio amplifiers as a coupling capacitor between two audio amplifier stages, and in speaker system to direct the higher frequency signal to the smaller tweeter type of signal speakers, while blocking the lower bass signals are also used as a filters to reduce any low frequency noises. So we'll use this high pass filter in audio amplifiers as a coupling capacitor between two audio amplifiers and stages, and to blocking the lower bass signals or noise signals from the audio frequency or audio range, any low frequency noises or rumble type of distortion. When used like this in audio applications, the high pass filter is sometimes called as a low cut or bass cut. Okay, so this is also known as a low cut or bass cut when we use in audio applications. Now the output voltage Vout depends upon the time constant and the frequency of the input signal as seen previously. With an AC sinusoidal signal applied to the circuit, it behaves as a simple first order circuit, high pass filter or circuit. But if we change the input signal to that of square wave, earlier we have given a sine wave or any DC wave. Now if I change it to the square wave shaped signal that has an almost vertical step input, so it will become a vertical step input. The response of the circuit changes dynamically and produces a circuit known commonly as a differentiator. So when I applied a square shape, now output will become a vertical step input. So this circuit or this arrangement is known as a differentiator. So if I see the RC differentiator, up until now the input waveform of this filter has been assumed to be sinusoidal, right? We have done for sinusoidal, or that of sine wave consisting of a fundamental signal and some harmonics operating in frequency domain, giving us a frequency domain response for the filter. However, if we feed the high pass filter with a square wave, now I am giving input as a square wave signal operating in the time domain, giving an impulse or step response input. So this square wave is nothing but either impulse or step response. The output waveform will consist of short duration pulses or spikes as shown. So if I give the square wave as an input, now my output will have spikes, it will shown like a pulse and with a spikes or distortion. So these are known as a distortion or spikes. So this is the arrangement. So at low frequencies we will got my output as a pulse with a spikes. At medium frequencies it will less reduced, whereas at high frequencies it will completely a pulse waveform, pulse type output. So each cycle of the square wave input waveform produces two spikes at the output. One is positive and another one is negative, and whose amplitude is equal to that of input. So any frequencies it will produce two spikes at output, like this is the positive and this is the negative. The rate of decay of the spikes depends upon the time constant. So this rate of decay means this rate of decay is depends upon the time constant, RC values. RC circuit time constant is nothing but tau equal to RC, value of both components, and the value of the input frequency. The output pulses resembles more and more shape of the input signal as the frequency increases. So if I increase the frequency, now the output signal is more like shape, it will become a complete pulse shape. Okay, so with this I am concluding this session. In next session we will discuss about active high pass filter. Thank you.